So let's apply everything that we've learned. And so we're going to combine circular motion with Newton's law of gravitational to develop a working understanding of orbital motion. And the orbits that we'll be talking about will just be circular orbits quantitatively. Qualitatively, you need to be able to deal with elliptical orbits. That's what the previous video kind of talks about. And we'll come back to that when we do energy. But I'm going to go back over something that they talked about in the video, because this is one way of understanding what's happening, why in a circular orbit you feel weightless. Going back to projectile motion, if you think about the horizontal projectiles, then the range determined, the range of the projectile was determined strictly by the initial velocity, v naught, over here. So the faster it goes at the beginning, the further it lands out. And we approximate the Earth to be flat for short distances. But what happens when we can't do that? When the velocity is fast enough that the Earth actually starts to curve? Well, then the object still continues to fall, but now it's going to hit a little bit later. And if we launch it even faster, then we can start getting it'll land around here, and so on, until you finally reach a velocity at which the rate at which it's falling, so the curvature of this parabola, matches the curvature of the Earth. And so it ends up falling all the way. I know I'm not drawing this very well, but it ends up falling all the way around. It's still trying to fall to the Earth, but the Earth keeps moving out of the way. Man, that is terrible. Okay, so anyway, it comes back, and that is an orbit. So it only depends on the velocity and how high up it is, the r, how high above the surface it is, and it's also determined by this r. But you get the idea. So at a certain height, I need a certain velocity, and then this free-falling motion will create an orbit around the object. So circular orbits. They're basically just free fall, or free fall. So when you're in the ISS, you have microgravity because you're just falling. It's the same as being in an elevator and the cable snaps. Well, you're in free fall. It's the same up here. So you're essentially just falling in a circle. I know it seems weird to think about, but that's what it is. Okay, so let's tie this all together, and then we can start quantifying some stuff. So first, let's go back the equations that we have so far. We have Newton's second. These three are all given on your equation sheet. So we have Newton's second law. The acceleration is net force over mass. Rearranging, the net force is equal to mass times acceleration. And then we have the definition of centripetal acceleration, which is v squared over r, and that's your tangential velocity. And then we have Newton's gravitational. And so we can combine these together in order to start dealing with orbits. Over here, these are not on your equation sheet, but the radius is Earth stuff. Let me see. I don't know if that's given or not. No, it's not. So anyway, if you need it, it'll be given to you. The radius of the Earth, 6378 kilometers. And the period, so the period for circular motion is 2 pi r over the velocity. So the distance, that's the circumference around a circle, distance divided by the velocity. That will give you the time it takes to do a circle. We'll come back to this one. So first, let's combine some stuff. So here's the Earth, and if we had some satellite moving in a circular orbit. So it's in a circular orbit. This is constant. It's uniform circular motion. And so we know that there's a centripetal acceleration. So we have to have a centripetal force here. And keep in mind, the centripetal force is a net force. So it can come from multiple or it can come from just one. But we know that there's a net centripetal force here. So up here, what I'm going to do is I'm going to take that. And so it says that the net centripetal force is equal to the mass. And since we're dealing with acceleration, it's going to be times the centripetal acceleration. So what this does is it combines these two together. And so we use Newton's second in terms of a circle. Now we just have to figure out what this centripetal force is. And in the case of a satellite, that force is simply the force of gravity. So now this one comes in. So we'll substitute over on this side. So the force of gravity is the net centripetal force, and that's mass times the centripetal acceleration. Now here's where you will tend to mess up, is you'll change Fg into mg, and then you get centripetal acceleration is equal to g, and that's not true. We have to use Newton's law of gravitation. So big G, m1 over m2. You know what? I'm going to change these, because instead of putting mass 1 and mass 2, we're going to use the mass of the satellite. Because this one up here, this is mass of the satellite, and the mass of the Earth. Those are our two objects. Divided by r squared is equal to the mass of the satellite times v squared over r. All I did was substitute the definition. Okay, now we can cancel off the mass of the satellite. That doesn't matter. And then I can move this r squared over to the other side. So we get g times me equals r squared would be up top, so it would be v squared r squared over r. We get g times me equals v squared. This cancels one of those times r. Okay, so I just wanted to do this in order to build a relationship. Over on the left-hand side, this g is constant and the mass of the Earth is constant. So this entire thing is constant. And what that means is over here, these are indirectly proportional. So if the radius goes up, the velocity has to go down, because it has to be the same number on the other side. The other way to think about this, if I moved r back over, this would be gme, the constant, times, I would have to divide, so it'd be 1 over r is equal to v squared. So we see that v squared is proportional to 1 over r. So the further away you get, the slower the object goes. So you have slower velocities up higher, away from the Earth. So it'll slow down. Very close to the Earth, it's very quick. And we'll do that. So we'll do a period so that you can see like the time it takes to go around. Well, anyway. Okay, so let's apply it. Let's talk about the ISS. So the ISS, I'll come back. Actually, we're kind of done with that. So the ISS, the International Space Station, it orbits around 400 kilometers above the Earth's surface. And what I want to know is, what's the velocity? How fast is it going? And how long does it take to go around the period? Okay, so if we have the Earth, then we'll have the ISS. And it's actually really low. It's only 400 kilometers. Now, you have to be careful here, because the r that we're going to have to use is the combined r, because it's to the center of the Earth. It's this r. So the r of the satellite would be the radius of the Earth plus the 400 kilometers, and we have to put that in meters, so plus 400,000. Now keep in mind the radius of the Earth was, what, like 6,000 kilometers? Yeah. So it's 6,378,100 kilometers plus 400,000. So you can see this is this doesn't change this one very much. It's 6 million to get up here, and so it's actually the space station is very, very close to the surface. So that's the satellite. So whatever that is, I think it's what we just add 4. So 6,778,100. That would be r to the ISS. Okay, using Newton's second law. So when we do these, you start with the second law. So the net force is equal to the mass of the satellite times the centripetal acceleration. And so that would be centripetal force. And the centripetal force is just going to be the force of gravity, mass of the satellite. I know I'm doing this again, but that's what it takes. You just do it over and over. Force of gravity is big G. And then we have the mass of the satellite, the mass of the Earth, divided by r squared is the mass of the satellite, times v squared over r. And what we're going to do is we're going to find the velocity first, and then we'll use that to get the period. The mass of the ISS goes away, so the mass doesn't matter. We're going to have the same, any orbit at a certain height is the same velocity, circular orbit. Moving this one over here, we get g times the mass of the Earth divided by r. I moved this one up here, and it canceled one of these. That's equal to v squared, so we got to take the square root on this side. Oops. So the velocity, the orbital velocity of the ISS would just be g times the mass of the Earth divided by r. The mass of the Earth, it's like 6, let's just say 6 times 10 to the 24th. So the mass of the Earth is going to be 6 times 10 to the 24th kilograms. So if we plug in that numbers, g is your gravitational constant, which you already found, 6.02 times, what is it? I can't even remember. It's given 6.67 times 10 to the 0.67 times 10 to the negative 11. And mass of the Earth, and then the r is going to be the rs, this quantity. You plug all those numbers in, and you get a velocity of approximately, see my calculation, 7,686 meters per second, which is 7.686 kilometers per second. So every second it travels over 7 kilometers. So it's fast. It's moving very fast. And the reason it's moving very fast is because it's very low. It's very close to the surface. Well, I won't get into that. Okay, let's figure out the period. So we know it's going really fast. That's the velocity. But what's the period? So the period would be 2 pi r, then that's of the satellite, divided by the velocity. So it'd be 2 pi times this divided by this. If you do that, you get approximately 5,540.99 seconds. And that doesn't make much sense. So let's convert it. So if we divide by 60, we can get it into minutes, which is equal to approximately 92 minutes. So what that means is that the space station makes a complete orbit every 92 minutes, about an hour and a half. It goes all the way around the Earth. So that's about an hour and a half, 1.5 hours. So if you divide 24 by 1.5, you get about 16 orbits per day. So if you stayed up for 24 hours on the ISS, you get to see the sunrise over the Earth 16 times, or set, I guess, depending on what your preference is. Anyway, pretty fast, right? So you can actually look it up. You can actually look up a map. I don't know if you've ever seen the ISS. Let me see. You can just Google ISS location. One of these live space station tracking. Let's see what this is. Spot the station, nasa.gov. Sighting opportunities. So, I don't know how this works. Let's see. El Paso, Texas. Well, I don't know what this 12 is. Zoom in. What's this? 3. view sighting. So at the Chum is all. Let's see, today is the 5th, so on the 8th at 7:30 in the morning, for 3 minutes, you'll be able to see it. Max height 13 degrees. So there you go. You could actually just use this, figure out a location. This would be anywhere. This just would be easier to see. So notice it's not visible for very long because it's going very fast. You see how quickly? You're like, whoop. All right. That's it. So that's our basic orbitals is this right here. This is the important part. This is how you solve these problems. We can ask for anything, but it's right here. Actually, it's probably there, because then it depends on what you're looking for. Like we could give you a velocity and you tell me how high it's got to be. Or if we know the velocity and how high, we could determine the mass of whatever object it is. But it's basically this right here. This is what you need to be able to deal with. And that's it. One last thing I forgot to mention was Kepler's third law. Third law, which he says the period is proportional to the cube of the distance. And what I want you to do, I'm not going to do it, is show how this comes from Newton's second law. So I want you to go from Newton's second law to Kepler's third. Newton's second being the net force is equal to the mass times the acceleration. So you'll have to use that. And then you'll have to use the definition of the period, 2 pi r over v. And remember, this is all centripetal. We're talking about orbits here. So start with this stuff and get to that it's proportional to r cubed. I'm sorry, it's the square is proportional to the cube. So you'll get to this square.